Hey, this is Mr. Woodward going through the notes on magnetic force and right-hand rule number 2. So I am assuming that you have already watched the video for magnetic force on a particle. If you haven't done it yet, check that out now. That video introduced you to the second right-hand rule. And the second right-hand rule relates the magnetic force on a particle if it's moving through a magnetic field. So in general, I have this little visualizer. This is a bed of nails that a student made for a project years ago. But imagine that this bed of nails is a magnetic field that's pointing towards you, and that this tennis ball is a particle, could be a proton or an electron, needs to be a charged particle, can't be a neutron. This doesn't work if it's not charged. That's moving through the field and moving perpendicular to the field this way or even this way. This wouldn't work if it was moving this way or this way. That would be parallel to the field. And the idea is that if you have a charged particle moving perpendicular to a field, then it will experience a force, and that will cause the particle to turn, move. And so right-hand rule number 2 explains, using your right hand, how to determine the direction of the force on that particle. So this is visually challenging. So the first thing that I want you to do is we're going to identify these 6 directions. So this is obvious, it feels obvious, but write it down on your paper anyway. This direction is up, this direction is down, this direction is left, this is right. This is going to be a direction into the page, right? Moving this way. This is going to be the symbol for something moving out of the page, moving this way towards you, okay? And so the big idea is that if a charge moves through a magnetic field at an angle, meaning a charged particle, it feels a magnetic force. The direction of that force can be determined using right-hand rule number 2. And so here's a picture of that. And this is how it works. If you take your right hand, your 4 fingers will represent the direction of the magnetic field. Your thumb will represent the direction that a particle is moving. It could be moving as like an isolated particle, or that particle could be moving as part of an electric current, like flowing through a wire. And then the third direction is shown by the direction that your palm is facing. And so I have a 3-dimensional set of crayons that show that, okay? The first direction in the 4 fingers, the second direction is going in the thumb, and the third direction is coming out of the palm, okay? They are all at right angles to each other. So we're going to use this to help us determine the direction of either the force on a particle, or maybe there's an unknown magnetic field direction, or maybe there is an unknown direction that the particle is moving. Here we go, starting with example 1. So a positively charged sodium ion moves upward through a magnetic field that's coming out of the page, as shown below. Which direction does the ion get pushed by the magnetic field? And so this picture here is a picture of what I have right here. We'll pretend that this is our sodium ion. This is the magnetic field that it's immersed in. It's coming out of the page, and that the ion is moving this way, upwards, okay? So let's use the right-hand rule to figure out the direction of the force, right? Which direction does the ion get pushed by the magnetic field? So first, write this down, the direction of the 4 fingers, the thumb, and the palm in order to illustrate this. So the 4 fingers are going to move in the direction of the magnetic field, which is shown by all these dots. That's coming out of the page. Then the thumb is going to go in the direction that the particle is moving, up. Now that's up, right? Up according to the page. I don't mean up this way. I mean up according to the page direction. And then if you do that, 4 fingers out of the page would be this way. Thumb up would be this way. Now my hand wants to slap this way, right? my palm is facing that way. So palm faces to the right, meaning the right of page, which means that's the direction of the force, right? The palm is the direction that the particle will be pushed. And so I'm going to draw a force arrow to the right on this one. Let's keep going. Second example. Suppose a proton hits our Earth's magnetic field, as shown in the picture below. Which way does the proton get pushed? Okay, so here we go. 4 fingers are going to be pointed in the direction of the magnetic field, which is to the left. The thumb is going to point in the direction that the particle is moving, which is down on the page. And therefore, the palm is going to be like this. Well, 4 fingers left, thumb needs to be down this way, and so my palm is going to slap into the page. Okay, the particle will be pushed this way. That is this direction, right? Into the page, the X. So I'm going to use that. I'm just going to like draw an X over it and label it with F. That's the force. So as the particle is moving down this way, it's going to want to like curve inward into the page. Let's keep going. Example 3. Which of the following feels a force in a magnetic field? Circle all that apply. So these are the 3 criteria necessary in order to create a force. A force is produced from, number 1, charged particles. Particles have to be charged. Number 2, a force is produced from charged particles that are moving. They can't be staying still. And produced from charged particles that are moving perpendicular to a magnetic field. Can't be moving parallel to the magnetic field. So here we go. An electron that is at rest in a magnetic field is not going to experience a force because the at rest doesn't work. B, an electron that's moving perpendicular to the magnetic field. Yeah, that works. C, a proton that's at rest. Again, at rest doesn't work. C is incorrect. A proton moving perpendicular to the magnetic field. Yep, that would also experience a force. Letter E, a neutron. A neutron is not charged, so that's not going to generate a force. And it's also at rest, so that doesn't help either. And then F, a neutron moving perpendicular to the magnetic field. Again, it's not charged, so it's not going to work. B and D are the only right answers on that one. Finally, example 4, the next video is going to have me actually do this for you. A straight wire with current flowing through it is placed in a magnetic field as shown below. Which direction does it get pushed by the magnetic field? Your teacher should be able to demonstrate this to you, so check out that video. So this is a north pole, this is a south pole. The magnetic field is going down, and then this is the letter I, which denotes the direction of current. So current is flowing in like a wire to the right. So here we go. Your 4 fingers are going to point down in this example. Your thumb is going to point in the direction that the particles are moving, right? Which is the current flowing in the wire to the right. And if you do that, your hand will look like this. 4 fingers down, thumb to the right, like that. And therefore your palm goes into the page. The wire is going to get pushed in this direction. And then what would happen if the direction of current was reversed? Well, if the direction of current is reversed, now instead of current going this way, current is going to go that way. And so the direction of the palm would now be outward. So we would say that the force would be out of the page. And I forgot to label the force which is into the page here. I could show that by drawing these X's, right? And labeling them with F for force to say that the wire is going to get pushed this way. All right, check out the next video for this final demonstration. Thanks for watching.